Solving systems of linear differential equations using matrix methods. The outline that I'm going to try to go through today is differential theory with using matrix methods. Try to work an example and some additional theory and another example. Now, this problem I'm working on is not going to be covering all problems, every type of problem that is. This is really a differential equation with constant coefficients with a force, kind of a force function on the end of it, but it's actually a column vector. So this is not the end to all end way to solve a system of differential equations. There's many considerations with matrix, the type of matrix, the type of differential equations. You have to take those things into consideration. So this is more a simple problem, and actually a 2x2 matrix, which is 2x2 is relatively simple to deal with. Okay, so here's the system of differential equations. Just to give you an idea of the structure, how the notation is put together, you look at A, and you can compare the right side of the arrow. It's got a coupled differential equations with constant coefficients, and it's also coupled. It's coupled because you have an x1 variable in the x2 differential equation and the x2 variable in the x1 differential equation. And on the left side here, you can see how you can write this in terms of a 2x2 matrix and also a column vector. So you can shortcut. There's other ways of solving these type of differential equations, but there's using matrix methods is a shortcut of doing that. And B, you can see the structure. You can see how you can multiply which is a homogeneous differential equation, or homogeneous system of differential equations, and you can see how the column vector is structured, more or less the template, and you can see the notation that is similar to like vector notation that you would probably see if you're taking physics-based calculus or just vector analysis. Okay, in solving a system of differential equations that are in-homogeneous, the first thing you need to do is you need to solve the homogeneous versions. That means removing the force function. That means removing the force function. In that case, in the previous chart, there was that additional column vector out there, which is the force function. Now, the solution to the homogeneous equation is in equation 2, which is phi phi is a function of t, and you have c, which is c is more or less a column vector or a constant. Usually, in general solution to a differential equation, you don't have any initial conditions, so uses a general solution, and there is more than one solution, which you use constants to write out the general solution. Now, if we write the homogeneous equation in vector notation or matrix notation, you'll see how it's written in vector notation. You can see what's represented the derivative on the right side, on the left side, the matrix A, right side of the equal sign, and the column vector X, which typically represents what we looked in the previous charts, x1, x2, and the force function, which is a function of t, which is typically a column vector. Now, the particular solution to an inhomogeneous equation is actually what is saying a particular solution. The way to write it is there's an additional with the homogeneous solution. There's an additional function of t multiplied with that general solution. So what you do is you take the particular solution and you substitute it in equation 1. So that's equation 4 into equation 3. And what you get is, you can see where I simplified the equation, and you see the force function on the right side of equation 6. And now what we have to do is, in the next chart, is we know that this is given this function, which is a 2 by 2 matrix, is true. The derivative of this function is true. This is a true property. So we use that and we substitute that into the equation, and we simplify, and we go all the way down here to equation 9a, and look at what we have. We have a differential equation, and keeping in mind that it's a matrix equation, not a scalar equation. So we have to be careful when we multiply and divide. So looking at 9b, if you know about linear algebra, you know you have to take the inverse of that matrix on both sides, because the matrix may not be commutative, have a commutative property. So and you solve for u, which you solve for u prime, and u prime is actually a matrix differential equation. And you see the identity matrix in equation 10, and on the left side. And of course, that's just, multiply an equation matrix by its identity, you get that same matrix back. So you integrate both sides. So integration applies to each element in the matrix, which when in this case, you have on the right side of equation 10, you have a 2 by 2 matrix, and then you have a force function, which really is a column vector. So that's a 2 by 2 by a 2 by 1, and you have to get a 2 by 1. So if you have to go back to review linear algebra, understand what I'm saying. I'm pretty sure you understand matrix multiplication, because if you don't understand matrix multiplication, you would not understand this whole presentation. So when you solve for u in equation 11, you get an integral equation. So you find the particular solution, which is a ut. Ut is substituted right back into the earlier equation of particular solution. You have the particular solution, which is what you have in look at it first, equation 12. You have the summation of the general solution and a particular solution, and that simplifies into equation 13. You have the more details of the general solution and the particular solution. So this is a matrix equation or matrix solution with a constant coefficient column vector, which is, you multiply that column vector by the 2 by 2 matrix, and you're going to get a column vector. This integral equation, you multiply the inside of the integral first, which is a 2 by 2 by a 2 by 1. So whatever you're integrating is, you're integrating a column vector inside that integral. So once you get that integral and calculate the integral, then you multiply the column vector by the 2 by 2 matrix, which is phi of t, and you get a column vector. So you can see that in equation 13 that you have a solution. You have a total solution, which is a column vector solution. Okay, so going back, we're going to test this out and see what we get. And so what we do here is we have an example of a differential equation, system of differential equations, which was really the early example of just showing what these type of equations look like. What you first do is you first solve the homogeneous equation, solve the homogeneous differential equation. So you solve the homogeneous differential equation by finding the eigenvalues and the eigenvectors of the coefficient matrix. And the coefficient matrix is, what you have here is the -3 in the first row, first column, 2, 1, 2, and -4. So that is, you got to find the eigenvectors and eigenvalues of that matrix. Okay, and finding the eigenvalues and eigenvectors, once again, I'm assuming that those who are looking at this presentation understand finding the eigenvalues and eigenvectors of a matrix. So I'm not going to go into detail into that. So that's something that I maybe could do a presentation on, but I may leave that to the great the mathematicians. But in finding the eigenvalues and eigenvectors, you find the eigenvalues first, which the eigenvalues are -2 and a -5. Now, using those eigenvalues, you can get the eigenvectors. And the eigenvectors in this case is 1, 1 and 1, -2. But your solution vector is structured in the fact that you have in this case, in these types of equations, it's the column vector times the exponential of the eigenvalue. So you see that in equation 17a, and you see the total solution, which is in 17b. And you can form the phi matrix. Because remember, again, we're only solving, this is the solution to the homogeneous equation. We're trying to get the solution to the inhomogeneous equation. So you form the phi matrix, and that's where you have, here's the phi matrix, which you got e to the -t, e to the -5, t, which is in row 1, column 2. Just for a point of reference for that matrix. Okay, we have to find the inverse of the matrix. And so in the phi matrix. So in finding the inverse of the phi matrix, this is just what you do for a 2 by 2 matrix only. You exchange the diagonal. The diagonals elements are 2, 3, e to the 2, 2t, and -1, 3, e to the 5t. They got switched up in this. So that if you go back and look at the matrix, you can see the comparison, how the diagonals got switched up. They switched diagonal, and you take the negative of the matrix. You take the negative of the matrix. The negative of the matrix. So when you calculate this, and let me look at, yes. And you also, these are the negatives of the off diagonals. The negatives of the off diagonals. Okay, so when you calculate this, you do this calculation, which is remembering, and this is just a particular solution, you see where you have in equation 19 what you have to do. Okay, here's a more simplified version in the calculation when you put the the 2 by 2 and the 2 by 1 matrix together. All right. So also, you see the matrix on the outside of equation 21. And you further simplify this, you can see the calculation, you have the particular solution. Here's a particular solution. And you further simplify it. And here's the solution in one form of equation 24. You can see that you have a matrix multiplied out, but you can separate these out into column vectors. You also, in the first part of the general solution, you have the matrix with the column, column vector, which is the constant column vector. As I mentioned earlier, how the C vector is structured, C1, C2. So you see in equation 25 how all this can be separated out. And this is your solution. Okay, additional theory. Well, normally, typically, sometimes you have these equations. You also will have the initial condition. You have the initial condition. And equation 25 is what you consider the initial condition, because the solution of the homogeneous equation, you can have you can have the initial condition being this right here, equation 25. See the initial condition. So what you do is you solve for the constant vectors, and you get what the constant actually has to be. And you see in equation 26, now, well, equation 27, you now have a solution. A solution of the first part, what they call a solution with an initial condition. In the second part of that equation, you have a definite integral. Now, the other problem that was solved in the example was an indefinite, because there was no initial conditions. This is the equation for a definite solution with the actual initial conditions. So this is the general solution. Okay. Now you look at equation 28 and in equation 29, you can see the comparison. Compare the two and see the difference. Indefinite 28, definite 29. So what else can we do? This is additional theory. What else can we do with this? Well, we do know in a scalar form in equation 30 that if you have a differential equation in scalar form, that its a solution is when you take the derivative of it, one solution of that equation is like equation 31, x equals to c times at. That's easy scalar. But it also somewhat applies in matrix form or vector form, column vector form. It actually applies in that equation. It applies. Same thing, principle applies. But there you have to be careful, because now that your solution is what they call a matrix exponential. It does not necessarily have all the properties of the scalar exponential. So we have to be carefully deal with the A matrix. Equation 32 is a comparison of the scalar versus the matrix differential equation. Similar. Now, in equation 33, you see the solution to that to the homogeneous equation. That's not including the forcing function. Now you can see on the matrix version of the solution, which is that e to the at and a being a coefficient matrix, you can see that the solution is written a particular way, because with the multiplying the matrix, you have these matrices, they have to be the right correct size. So here, for example, you need to have a 2 by 2 with a 2 by 1 column matrix for to be able to do the matrix multiplication, as opposed to on the left side here, you have a scalar. Scalar is commutative. You got x equal to c plus e to the at, small a, e to the at. I can take that c and move it to the right side. It doesn't matter. But in this case, in the matrix solution, that does matter. You have to be careful with that. And here's equation 34 is the series representation of the matrix exponential. I don't discuss all the series properties here, but something you may want to look up to get a better understanding. Now we know that in this case, this is a non-singular matrix. Non-singular matrix. Because this applies to, we're applying this to a system of differential equations. Okay, you can see in equation 35, you can see the comparison. That's a comparison of the general and particular solution with the matrix version of the general and particular solution, with both including the forcing function. Very similar, very similar. Now, some of the equation 36, you just have I've listed some properties of the matrix exponential that apply, that are true. That last thing about uh, the inverse also applies. It definitely applies. Uh, Consider that carefully. At least I did. And since we know it makes it, you look at a differential equation, especially homogeneous, uh, the matrix solution just seems to fit well. It seems to be easier to deal with. But the matrix solution, what is an exponential matrix? You know, that looks more. It actually looks more complicated, and we need to find a better way of dealing with that. Uh, Not actually using that matrix, trying to calculate the matrix exponential. Now you also see some other features of the matrix exponential solution. Now we have to be careful about uh, the multiplication of two matrices, exponential matrices, because that's generally not true. You can see that e to the b times e to the c, them being matrices, is not generally equal to e plus bc. That's not necessarily true for all matrices. So we have to be careful of that. Uh, but we know that, especially on the scalar exponential, when t is equal to 0, we get the exponential is equal to 1. But for the matrix, it actually equals to actually identity matrix. Now, the other way to doing this, to trying to solve for uh, the condition, which is the identity condition for the exponential solution, is to solve for the coefficients uh, with the identity matrix. Actually, you use algebra and solve for it. Now, the other way to doing it is using the fundamental matrix from, like we did in the general problem, the other previous problem, which we get the solution. And we just take that fundamental matrix and find and multiply the inverse of that fundamental matrix as a function of t naught, and we can calculate a new fundamental matrix, which we can use equations 37. And you can see equation 37, how similar they are. But the difference is that your fundamental matrix on the right side here, it's outside the integral. And on the left side, you have the difference of t minus s of the fundamental matrix. So what I'm going to show later is I was trying to do a comparison to see if do I actually get the same thing, same answer for the particular part of the solution for an example, similar example we did earlier. So I wanted to do a comparison on that, and you'll see that in upcoming charts. Okay, going back to the previous example we did earlier, you see the matrix equation with the forcing function, and you see the coefficient matrix A. You see that the eigenvalues, and we end up resulting in we had earlier in the fundamental matrix for that differential equation. Now, in equation 40, we have a different fundamental matrix solution, which is the matrix exponential solution, which we covered in previous charts. But in order for to this apply, we can't use the matrix in 39 because it doesn't. When you make t equal to t naught, it does not, or t equal to 0, it does not come out to the identity matrix. So in order to calculate the new fundamental matrix related to the matrix exponential solution, we have to calculate use the fundamental matrix in equation 39 and multiply it by the inverse as a function of t naught, and we'll get the new fundamental matrix, which is related to the matrix exponential solution. And you see that I actually go through and do this in equation 42, in equation 43. Equation 44 is the calculation of the fundamental matrix, and you use the phi matrix to calculate the fundamental matrix. The phi matrix and the inverse of the phi matrix as a function of t naught, and t naught being relating to the initial condition of the problem, which is the coupled differential equation problem, which has an initial condition. Now, if you substitute in t naught in for t, you should get the identity matrix, which that, remember, the exponential matrix, which was the solution to the differential equation, the matrix solution to the differential equation, the initial condition had to be equal to the identity matrix. And you check this matrix and you'll see that you have that. Now, you have to calculate the inverse of the fundamental matrix and multiply by the forcing function column vector. So in order to do that, to find the inverse, you need to calculate 1 over the determinant of the matrix, fundamental matrix, and for us to change the diagonals and take the negative of the off diagonals. And you see that in all this in equation 45. Okay, equation 46, which is a column vector. This is part of the particular solution, which it's before you take the integral. Now, the first two terms of the top and the bottom of the column vector, the two terms, you see you have an S and an exponential function. So you're going to have to end up doing the integration by parts. And we also were calculating a definite integral. So this is why in the equation 47 and 48, I use Mathematica to do the integration, because I thought that would be easy. Now, the reason why I'm doing that is that I wanted to do an easy calculation to do a comparison to what we're going to see later, to the fundamental function, which is not the inverse, but the fundamental function fundamental function matrix which is a function of t, and you multiply that by the inverse of that fundamental function, which is a function of s, and you get the function, fundamental matrix function t minus s, and see what you get. See if those things are the same, are those terms the same as part of the particular solution. That's what I wanted to check, and you'll see what I get coming up later. Equation 49, you see the matrix. This is the version of a particular solution which you bring in the fundamental matrix, which is a function in t, function of t, which you can bring it within the integral of the particular solution, because when you integrate, you're integrate as a function of s, not t. So what I did was I calculated this version, which is before taking the integral on, you see equation 50. You see what I have here. Equation 51 is just a reminder of equation 50 on the last slide. So when you multiply the column vector with the 2 by 2 matrix, equation 52 is your result. This is what you get, a 2 by 1 column vector. Equation 53 is a result of multiplying the fundamental matrix t minus s times the column vector. This is before integration. Now, when I integrated, the results I got was equation 54, 55. Now, what I have in the previous charts of the multiplication of the inverse fundamental matrix as a function of s times the column vector fs, that is, those results after integration should not match up with what I have here, because in the previous chart I didn't multiply the fundamental matrix. When I do that, I should get the same results as equations 54 and 55. Now, I didn't do that here, but I may do that at a later date and put it on Patreon, and for those who want to see it, maybe subscribe to my Patreon page. But the results match up. So I wanted to present this problem because I thought it was pretty interesting. It would help somebody that's probably maybe looking for answers, doing DEs with using matrix methods. So hopefully this helps. Hopefully you'll subscribe to this channel. I'm hoping to do more types of problems like these, which would be something more or less advanced, graduate type problems in physics and math, but a little less. It could be used for research. Techniques can be used for research, but not research problems themselves. So I just thought this would be a very interesting problem that I encountered when I was doing some tutoring. So let me know what you think. Leave a comment.